Welcome to the deep dive. You're here, I imagine, because you want to get up to speed on large language models, LLMs. You want to understand them quickly, but, properly.
Right, get those aha moments without feeling like you're drowning in jargon.
Exactly. And that's what we're aiming for today. We've gathered some really key research, and we're going to distill it down.
Yeah, we've really gone through it to pull out the core insights, how these things work, how they've developed, and frankly, the pretty amazing stuff they can do now.
So let's quickly look at our sources. First, we've got a survey of large language models from RUCA iBox on GitHub. Think of it as a living map of the field.
And their actual survey paper, too, Zhao et al., 2023. It's a great reference point.
Definitely. Then there's the paper that kind of kicked off a lot of this OpenAI's Improving Language Understanding by Generative Pre-training, the original GPT paper.
A foundational piece.
Mm-hmm.
It introduced that whole pre-training and fine-tuning idea.
We're also looking at a comprehensive survey on pre-trained foundation models by Zhu and colleagues. This gives us a wider historical view, from BERT up to ChatGPT. Puts things in context.
It's good for seeing the bigger picture, how we got here.
And then we have a couple more RCVIFA documents. One's a bit more general on LLM aspects, and the other really digs into the scaling, particularly focusing on GPT-3.
And visually, we've got some aids, too. Logos from OpenAI, Meta, the big players.
Right. And diagrams, one showing reinforcement learning from human feedback, RLHF, super important.
Crucial for alignment, yeah. And another showing different learning styles. Fine-tuning, zero-shot, few-shot, helps visualize the concepts.
We've also got a table with Meta's OPT model sizes, gives you a sense of scale.
Plus some architecture diagrams for those interested. Retro switch transformer.
A comparison of RLHF and DPO, direct preference optimization.
And low array for efficient tuning. Knowledge distillation for smaller models.
Oh, and one showing LLM agents plus graphs on GPT-3's scaling performance. Lots to cover. So our mission, basically, is to piece together this story. The evolution, the techniques, the capabilities, all based on this research. Ready to dive in?
Let's do it. Starting with the basics generative pre-training, GPT, from that first OpenAI paper.
Okay, so what was the big idea there?
Well, the really core concept was this two-stage training. First, you have unsupervised pre-training.
Unsupervised meaning?
Meaning the model just reads like massive amounts of text, the internet, books, whatever. But nobody's telling it this is right or this is wrong. It's just learning the patterns of language.
Okay, so it's just soaking it all up. Grammar, facts, how words relate.
Exactly. It's learning the structure of language, implicitly picking up world knowledge along the way.
And then comes stage 2.
Then comes supervised fine-tuning. Now you give it specific examples for tasks you actually care about, like here's a question, here's the answer, or here's a review. Is it positive or negative?
Gotcha. So it takes that general language knowledge and focuses it.
Precisely. Adapts that broad understanding to specific skills.
And the tech that made this possible was the transformer, right?
Absolutely. The transformer architecture was a huge enabler. It's really good at tracking relationships between words, even if they're far apart in the text. Long-term dependencies.
Which older models struggled with.
Yeah, older recurrent networks kind of lost track over longer sentences or paragraphs. The transformer's attention mechanism lets it weigh the importance of different words across the whole input.
And during that first pre-training stage, what's it actually doing?
The main objective is just language modeling, basically predicting the next word in a sequence given the words that came before.
Like autocomplete on steroids?
Kinda, yeah. But by constantly trying to predict the next word accurately across billions of words, it's forced to develop a really deep statistical understanding of language.
Okay. And the specific model they used back then?
It was a transformer decoder-only model. 12 layers, 768 dimensions for the internal states, 12 attention heads. They used atom optimization for training, byte pair encoding for the vocabulary.
Wait, byte pair encoding?
Yeah, it's a way to break words down into common subword units. Helps handle rare words and reduces the overall vocabulary size needed. And they use GELU activation functions. Little details, but they add up.
And the text it learned from, you mentioned books.
Right, the books corpus data set. The key thing there was it contained long, contiguous stretches of text, which they thought would be better for learning those long-range dependencies we talked about.
Makes sense. And they measured how well it learned.
Yeah, they reported a low perplexity score, 18.4. Perplexity is basically a measure of how surprised the model is by the text. Lower means it's better at predicting the next word.
So 18.4 was pretty good. indicating it understood the book's corpus language well.
Exactly. It showed the pre-training was effective.
Okay, so you have this generally smart language model. How did they then specialize it for tasks like understanding sentence relationships or question answering?
They had this clever way of formatting the input. For different tasks, they'd concatenate the relevant pieces of text like a premise and a hypothesis for inference tasks, but they'd add special delimiter tokens in between.
Ah, so like little signposts for the model, telling it which part is which.
Kind of, yeah. It helps the single pre-trained model structure the input correctly for different downstream tasks. For similarity, they might even feed the input in both orders to make sure order didn't matter. For Q&A, they'd combine the context paragraph, the question, and potential answers again, marked out.
Clever. And did it work? What were the results?
They were really strong, especially on natural language inference NLI tasks. The paper showed significant improvements over the state-of-the-art methods at the time on datasets like SNLI, multi-NLI, Scitail, QNLI.
So one general model was beating specialized models.
In many cases, yes. That was the big headline. It really suggested this pre-trained then fine-tuned approach was incredibly powerful. A generalist could outperform specialists.
Were there any caveats?
Well, they did note it underperformed a bit on one smaller dataset, RTE, which maybe suggested that for very low data tasks, some specialized architectures might still have had an edge back then.
And they tested why it works so well.
Yeah, they did ablation studies. They tried removing the pre-training step or changing parts of the model or training to see the impact.
And the conclusion.
It really confirmed that both the unsupervised pre-training on lots of data and the specific language modeling objective during pre-training were crucial for the success.
Okay, so that's the foundation, GPT-1. How did we get from there to, well, the giants like GPT-3, the RUCI box survey, and the GPT-3 paper tackle this, right?
Right. The RUCI box survey actually has a neat little evolutionary graph, kind of showing the lineage from GPT to GPT-2, GPT-3, and so on. Shows how research built on itself.
And then GPT-3 hits the scene. That seems like a major inflection point.
Oh, absolutely. Both surveys highlight GPT-3. 175 billion parameters. Just the sheer scale was unprecedented.
And it wasn't just bigger. It could do fundamentally new things.
Exactly. That massive scale led to what they call emergent abilities and, crucially, in-context learning.
In-context learning. Let's unpack that. That's the thing where you don't need to fine-tune it anymore.
Pretty much. Instead of retraining the model for every new task, you can often just describe the task in the prompt, maybe give it a few shot examples right there in the text input, and it just figures it out. No gradient updates needed.
That sounds incredibly powerful. Just tell it what to do.
It was a game changer. The GPT-3 paper showed it performing strongly on translation, Q&A, even reasoning tasks, just using this in-context approach.
Is that what figure 1.2 in their paper shows with the symbol removal task?
Precisely. It visually demonstrates how accuracy goes up just by adding a task description and increasing the number of examples K you provide in the prompt. And crucially, the bigger versions of GPT-3 benefited more from these examples.
In figure 2.1, contrast this.
Yeah, it lays out the different settings. 0 shot, just the prompt, no examples. 1 shot, 1 example, few shot, a handful of examples, and compares them to traditional fine-tuning, where you update the model weights. Uses English to French translation as a clear example.
So how did GPT-3 actually perform across different benchmarks using these methods?
They tested it extensively. On language modeling itself, like the PenTreeBank dataset, the zero-shot GPT-3 actually beat the previous state-of-the-art, which was pretty stunning.
Wow, zero-shot soda. Okay, what about other tasks?
On close tasks like Lambda, predicting the end of a passage, and completion tasks like story close or HelloSwag did very well, especially with few-shot examples. Figure 3.2 shows a huge jump on Lambda accuracy with just a few examples.
And question answering, like trivia QA.
Strong performance there, too. Its zero-shot ability was often better than earlier fine-tuned models. And with few-shot prompting, it got close to the very best systems, even those using external knowledge retrieval.
Translate.
Consistent improvement with model size and the number of shots. Figure 3.4 and those English to German results we saw show that trend clearly. Bigger model, more examples, better translation quality, generally.
What about trickier reasoning like Winograd schemas, resolving pronouns?
That was interesting. Fine-tuned models had gotten good on the original Winograd set, but GPT-3, even with few-shot learning, found the harder variants challenging. Shows the limits, perhaps?
Reading comprehension, answering questions about passages.
A bit mixed. It did well on some datasets like CoQA and Squad 2.0 in the few-shot setting, but less well on others like QuiIC and Race 8. Depends on the specific demands of the data set, it seems.
Super GLUE. That's a tough benchmark, right?
Yep, a collection of diverse tasks. And again, performance scaled clearly with model size and the number of in-context examples provided. Figure 3.8 illustrates that.
What about math? Arithmetic and stuff?
Ah, yeah. They tested things like multi-digit addition, subtraction, multiplication. The learning curves, like the one for single-digit 3-ops, show accuracy climbing with model size and few-shot examples.
But how was it with 0 or 1 example?
Quite weak, actually, which led them to suggest that maybe the model was actually learning the arithmetic rules on the fly during the test from those few examples, not just retrieving knowledge.
Fascinating, like learning at inference time.
Exactly. And even on synthetic tasks, like making up rules for manipulating letters or anagrams, giving examples in the prompt worked surprisingly well to teach the model the new rules.
So scale really unlocked this in-context learning phenomenon, but just being smart isn't enough, right? They need to be helpful, safe, aligned. That brings us to RLHF.
Yes, alignment is critical. The RUCA iBox survey and Figure 10 in the comprehensive survey detail reinforcement learning from human feedback, or RLHF. It's a key technique.
How does that work, roughly?
It's multi-step. First, you collect human demonstrations of desired behavior, like good answers to prompts, and fine-tune the base model on that. That's the supervised fine-tuning, or SFT step.
Okay, so you show it what good looks like.
Then you have the model generate multiple responses to various prompts. Humans then compare these responses, ranking them from best to worst.
Ah, collecting preference data.
Exactly. This preference data is used to train a reward model. This reward model learns to predict which responses humans are likely to prefer.
So it learns human taste, in a way.
Kind of, yeah. And finally, you use this reward model within a reinforcement learning loop, often using an algorithm like PPO, to further fine-tune the language model. The goal is to maximize the predicted reward, essentially steering the model toward generating outputs that humans consistently rate highly.
So it learns to be helpful and harmless based on what humans preferred in those comparisons.
That's the core idea. It was a major step beyond just predicting the next word, allowing for more direct control over model behavior based on human values.
And the RUA iBox survey mentions the La Mama family using this, and lots of research on alignment.
Yes, the La Mama model is built heavily on these ideas, and there's a huge amount of ongoing research in alignment tuning, exploring different methods, and refining RLHF.
Are there alternatives to RLHF?
Yes, the comprehensive survey mentions direct preference optimization, or DPO. Figure 30 contrasts it. DPO tries to achieve a similar outcome, optimizing based on human preferences, but without explicitly training a separate reward model or using complex RL algorithms. It optimizes the policy directly from the preference data.
Simpler, potentially more stable?
That's the hope, yeah. It's an active area of research.
Okay, so we've covered training and alignment. What about the underlying structures? The comprehensive survey talks about different LLM architectures, right? It's not all GPT-style decoders.
Definitely not. The survey breaks it down into 3 main categories. You've got encoder-only models, like BERT.
Good for understanding tasks.
Yeah, they process the whole input sequence at once, so they excel at tasks needing full context understanding, like classification or named entity recognition.
Then decoder only.
Like the GPT family. They generate text sequentially, predicting the next token based on previous ones. Great for generation, dialogue, that sort of thing.
And the third type?
Encoder-decoder models, like T5 or BART. These have both an encoder to process the input and a decoder to generate the output, naturally suited for sequence-to-sequence tasks.
Like translation or summarization. You mentioned T5 text-to-text transfer transformer. What was its big idea again?
P5's innovation was treating every NLP task as a text-to-text problem. Input is text, output is text. Whether it's translation, summarization, classification, you frame it all the same way for the model.
Just type translate English to German sentence, and it outputs the German.
Basically, yeah.
Yeah.
A very unified and surprisingly effective approach, though maybe not always the absolute most efficient for every single task compared to specialized models, but incredibly versatile.
And MAS and BART are other encoder-decoder examples.
Right. They use different pre-training objectives involving masking or corrupting the input text and learning to reconstruct it, making them very good at sequence-to-sequence tasks, too.
Okay, moving to specific model families. We know GPT, though the latest ones like GPT-4 are closed source, accessed via APIs mostly.
Correct. Fuzzer 9 shows how GPT-3's performance changes with the number of prompt examples highlighting that interaction model.
Then Google has Pollen.
Yes, the Pollen family, known for huge parameter counts, like Pollen 540b, trained on massive data sets, Very strong few-shot learners.
And flan palm.
That's an instruction-tuned version. They fine-tuned PALM on a vast collection of tasks phrased as instructions. This made it much better at following commands and generalized better across many tasks. Figure 14 gives a sense of that diverse instruction data.
The surveys list so many others, too. Cogen, Bloom.
Yeah, Cogen for Code, Bloom as a large, open, multilingual model.
Yeah.
Then newer ones like Zephyr, Mixtral with its mixture of experts.
Grok, Orca, StarCoder, MPT, Falcon, Gemini, DeepSeek Coder, DocLLM. It's a zoo.
It really is. The table in the comprehensive survey is great for getting a handle on their size, data, and whether they're open source or not. And we have that OPT table showing Meta's contributions to open models, too. It's evolving incredibly fast.
What's maybe one surprising thing about the sheer variety that stands out?
Just the speed of diversification, I think. We went from a couple of main architectures to this explosion of specialized models for code, for multilingual tasks, focusing on efficiency, using novel techniques like mixture of experts. It shows how much potential people see, exploring every possible avenue.
Beyond the core models, how are people making them better or more useful? The survey talks about augmentation techniques.
Right. Prompt engineering is huge now. Just figuring out the best way to ask the question or give instructions can make a massive difference.
That makes sense. And RA, retrieval augmented generation.
Yeah, RA is really clever. You basically give the LLM access to an external knowledge source. When you ask a question, the system first retrieves relevant documents or data snippets and then feeds those to the LLM along with your question.
So the LLM can use up-to-date or specialized info it wasn't trained on.
Exactly. It grounds the generation in external facts.
Yeah.
Very useful for reducing hallucinations and answering questions about recent events or specific domains.
And LM agents. That sounds like sci-fi. Models that can do things.
It's heading that way. The idea is the LLM doesn't just generate text. It can reason, plan, and interact with external tools or APIs. Figure 40 shows it being used for conversational search, breaking down a query, searching, summarizing.
Using specific prompting techniques.
Yeah, like ReWO or React, which guide the model through cycles of reasoning, acting, like using a tool, and observing the result to solve more complex problems.
Of course, the survey also covers the downsides, limitations, cost, adaptation challenges.
Absolutely. It's not all magic. Hallucinations, bias, computational cost are major ongoing challenges. And research is looking into cost-effective training, compression, better adaptation methods.
Let's talk data for a sec. Training these models requires unimaginable amounts of text. What are the key issues there?
Oh, plenty. Data cleaning is number one. Removing low-quality, toxic, or irrelevant text is crucial, but hard at scale.
And biases in the data.
A huge concern. If the training data reflects societal biases, the model will likely learn and perpetuate them. Addressing imbalances is vital. Then there's pre-processing, handling ambiguity.
Deduplication, too. Why is removing duplicates important?
It helps prevent the model from just memorizing common phrases or examples, improving its ability to generalize to new things. It can also reduce the influence of overrepresented data sources.
And tokenization, breaking text into pieces.
Yeah, how you tokenize impacts vocabulary size and how the model handles unknown words. Methods like BPE or sentence piece are common, each with trade-offs.
The survey also mentioned positional encoding. Why does a transformer need that?
Because unlike older models that process word by word, transformers look at the whole sequence at once using that attention mechanism. So they don't inherently know the order of words.
So positional encoding adds information about where each word is in the sequence.
Exactly. Early methods used absolute positional embeddings. Newer methods like relative positional embeddings or rotary position embeddings, ROPE, used in PALM and Llama, seem to work better, especially for longer texts. They encode position in a more flexible way.
Training these monsters must be incredibly expensive. Are there ways to make it more efficient, especially for fine-tuning?
Yes, that's a big focus. Low-rank adaptation, or lower figure 34, illustrates it is very popular. Instead of retraining all billions of parameters, you just train these small adapter layers. Much cheaper and faster for fine-tuning.
And knowledge distillation, figure 35.
That's about creating smaller models. You train a large teacher model, then train a smaller student model to mimic the teacher's outputs. You can get a much more compact model that retains a lot of the original performance.
Okay, so when the model generates text, how does it pick the next word? There are different strategies.
Right, decoding strategies. The simplest is greedy decoding. Just pick the single most likely word at each step.
Seems logical, but maybe boring.
Can be repetitive, yeah. Beam search is slightly better. It keeps track of a few top options, the beam, and explores them,
More diverse outputs.
potentially. And then you have sampling methods like TOCAC sampling, pick from the top pick most likely words, or top view, also called nucleus sampling.
Nucleus sampling.
Yeah, that picks from the smallest set of words whose cumulative probability exceeds a certain threshold p. This adapts dynamically. If the model is very certain, it picks from fewer words. If uncertain, it considers more options. Often leads to more creative and less predictable text.
Now, the elephant in the room. Hallucinations. Models making stuff up.
A major challenge.
Yeah.
Because they're probabilistic predictors, they can generate fluent, confident-sounding text that's just factually wrong. The survey mentions things like the veracity prior, a bias towards plausible-sounding statements, and their relative frequency heuristic favoring common but potentially inaccurate phrases from training data.
Still a big problem to solve.
Definitely. Techniques like RAG help, but fundamentally addressing it is ongoing work.
Lastly, the survey points to datasets and tools. We saw a table view with common sense reasoning datasets and frameworks.
Yeah, a whole ecosystem has sprung up. Libraries like FastChat, SkyPilot, VLLM for serving and inference, LangChain for building applications, vector databases like Melvis or Qdrant for RAG, Hugging Face's text generation inference. These tools are essential for researchers and developers actually using these models.
It really shows how the field has matured beyond just the core model research.
Absolutely. The tooling and infrastructure are key to making LLMs practical.
Okay. Wow. That was a lot, but hopefully a useful journey through the LLM landscape based on these papers. Let's try to wrap up the key takeaways.
Yeah, I think the big themes are clear. We've seen this incredible evolution, starting from that core GPT idea of pre-training, then fine-tuning.
Driven by transformer architecture and then just massive scaling.
Right. And that scaling unlocked unexpected things like in-context learning, changing how we interact with these models.
We also saw the crucial importance of alignment using techniques like RLHF or DPO to make sure these powerful models are actually helpful and safe, guided by human preferences.
And the diversity. Encoders, encoder-decoder architectures, and this Cambrian explosion of different model families, GPT, PaLM, Llama, Bloom, Mixtral, and so many others, open and closed source.
Plus all the techniques to augment them, RAG, agents, and make them more efficient, LoRa, distillation, and the ongoing work on challenges like data quality and hallucinations.
It's a field moving at lightning speed.
Absolutely. So this deep dive was really about stitching together those key insights from the research, giving you that solid overview without getting lost in every single technical detail, aiming for those aha moments.
Hopefully we hit that mark. So maybe a final thought to leave people with.
Yeah.
As we look at all this progress, the scaling, the alignment efforts, the new applications, what aspect of LLM development seems most critical or maybe most potentially transformative moving forward?
Is it just making them bigger? Or is it making them safer, more reliable? Or is it the creative ways we're starting to integrate them into everything?
Yeah, where do you think the biggest impact or perhaps the biggest challenge lies next? Something to ponder as this technology continues to reshape things.